So I'm going to very briefly through the lecture slide. What's going on, guys? Have you got a deadline? Why there's so few of you in the lecture? And there's only 14 of you online. What's going on? Huh?
There is a deadline.
There is a deadline.
Well, a 24-hour grace period. Deadline.
Come on, guys. The 24-hour grace period. That's incredible. You are incredible. You are incredible. I will not write you any reference letter because otherwise I will have to say that you can't keep up with your deadlines. So you keep using your 24-hour grace period on everything. Joking. Also not joking, but okay. So let's go here. There you go. This slide here. This slide, the strain energy due to the different kind of loadings. They are very easy to remember, but you don't have to remember anyway. And it's just an integral. So this works for beams, of course, because we made sure that this should be the integral of this beast here in dV, in a chunk of volume, in an infinitesimal volume. Now, for beams, the infinitesimal volume is always a dx. Okay, so that should not be an issue. Unless you have tapered beams, in that case, it's a of x in dx. So it's a function of x dx. But in this case, we're talking about straight beams of constant section, so everything is easy to integrate. But this is as general as it can be. So don't be afraid to use this for any kind of any other kind of shapes. That was the strain energy. Why do we need to calculate the total strain energy? That's because we have Castigliano's theorem. Castigliano's theorem is an easy way, always say easy way, but it's a convenient way, say, to calculate the deflection at a certain point of a structure if you know the total energy, the total strain energy of that structure. So the idea is that you take the derivative, the partial derivative of the total strain energy with respect to the force at which you have to calculate the deflection. Effie is asking, would we do a tapered beam in the exam? I mean, it's very hard to do these integrations without having any taper. So no, definitely not. Yes, I would like to give this in some sort of coursework for next year. Possible. Just give a complicated shape, say use Castigliano's theorem here, see what happens. But that's probably too nasty. So I'll think about it. And also I spoiled it already for you. And it's been recorded, so it won't happen. Yeah, that's a no. Don't worry. Don't worry. All right. Castigliano's theorem, that works for forces. If you're looking at deflection, you need to differentiate with respect to the force. If you're looking at rotation, this is orientation of the point. Then you have to differentiate with respect to a moment. But again, it doesn't matter. They're just symbols anyway. All right. Other things that we might be interested in are the simplified integration, where instead of differentiating the integral, you are integrating a derivative, which is much better to do. And for the other things, we can deal with curved components by rearranging ds as, if it's a circular component, that ds is always r d theta. But in that case, we must find what is the normal force as a function of theta, and the shear force as a function of theta, and the bending moment as a function of theta, as we did here, say m of theta. And finally, the last thing is you can find reaction forces by setting whatever deflection that you get from Castigliano's theorem equal to 0. If the force to which you are differentiating is unknown, and you know it's a reaction force, that means it must be equal to 0. So this thing is a single equation in a single unknown. It doesn't look like so, but it is a single equation in a single unknown. Very last thing, if you want to find what's happening in a specific direction to where a force is not applied, then you have to apply a force there. It's a fake force, it's a dummy load. And then you have to treat it as a real force until you get to the very last step. When you get to the very last step, you remember that was a dummy load. So you set that force equal to 0. and whatever term that has that force cancels out. Whatever does not depend on that force is what is effectively a deflection. Okay, so I think we wasted a bit of time in this. So let's solve the tutorial questions. I'll go here and I'll go here and I'll open this. And the tutorial I want to talk about is, well, this one is very easy because this is a pin jointed frame. So these only have axial force. Remember pin jointed frames? They only feel axial forces. So the strain energy is the sum of the axial force in this beam plus the axial force in this beam. It's not very complicated. This one, though, this has a bit of everything. This has a curved component, and it's a symmetric structure with two forces P and P. So we have to show that the deflection caused by forces P applied at the free ends is this. So this is the same thing, more or less, that you will get at the exam. In the exam, you more or less, I will either give you the energy or give you the deflection, and I will ask you to verify that this is correct, rather than find the deflection. Because in that way, I'm kind of guiding you a little bit. And I believe it's easier to calculate as well. So you should not spend much time on this. All right, so let me draw this on my screen. So this is a fixed thing. Then we have a circle, an arc of circle, really. And then let me disconnect this one. This one. Okay. So this is a radius of R. Very important because we must know the entire geometry of this thing. And it has a length of L. And the two forces applied are P and P. Now, as you can see, this is completely symmetric along this axis, this horizontal axis. And so instead of studying the entire thing, I will study half of it. I will study half of it. And that half is the top half. Why? Why not? So we'll get rid of this. And I'm studying just the top half. Of course, this will be a fixed support. Do you agree with me? Because that's a welding. And the welding, it's like if these two halves were welded together, and the welding is like an internal fixed support. Okay, now I have to ask myself, what is the strain, the strain energy of this beast? This is L. So first of all, I need to calculate bending moment and shear force and normal force of everything. Of course, there is no normal force in this bit. There might be normal force in this bit. Okay? Okay. So let's calculate. Now, you should agree with me that probably the best way of studying this is to study this from here to here first. So this would be segment 1, and this would be segment 2. Okay? With my x axis going from here to here. This is my x, okay? The origin here. So if I cut here and look right, because it's easier, to look right. I have, well, I'm not writing anything here, so let me write cut and considering just the top half of the symmetric structure, cut and look right for segment 1. So for segment 1, I am cutting and looking right, so I have to draw just this chunk. That's whatever is left. From the cut, that is here, this is the force P. And the internal loads are N of X, V of X, and M of X. You should remember these from year 102 MA. And of course, this distance is X, as I just said. So let's write the equilibrium equations. And then I have that N of X is 0. You agree with me that there is no horizontal force to balance? V of X is minus P. And then M of X is P times X. Okay, I'm not writing the entire equation, I'm writing the solution already. You can write the equations yourself. At this point, I believe you should be able to write equilibrium equations. Okay, minus Px. Why do you think is minus Px? Roberts. I believe it's plus Px. Because the moment oriented in this way is exactly counterbalancing the moment of P. So I don't have to change the sign of M. So this moment here is Px, and it's clockwise. Sorry, counterclockwise. So M of X must be clockwise in order to counter it. So M of X in this direction is Px. Right, so that's it. Let's do the other one, the other bit, segment 2. Segment 2 is a curved beam. So now segment 2, and I have to cut and look right. Cut here and look right. Let's call this point A. It's called, well, let's not call it A because A is moving, so let's not call it A. Let's cut in segment 2. Cut in segment 2. And look right. See, I must look right because if I look left, I need to find the reaction forces at the fixed support. Because if I look left, I have to draw this. If I look right, I have to draw everything here. But let's draw everything regardless. So if I cut and look right, I get this thing. Actually, let me copy it. If I cut and look right, I get this thing. This is P. This is L. And I have to cut everything that is on this side here. There we go. Remove everything here. This is still R. Where was it? Here. And here I have, again, the normal force. And in this case, it's n of theta, because it's a curved component, so I want it as a function of the angle, because this cut is moving angularly now. It's not moving in a straight line. And I want v of theta, which is, of course, perpendicular to n of theta. And I want m of theta. Okay. And this angle theta is this angle here. So let me forget about this, because I know this is a radius of r. So the angle that I'm looking at is this one. This angle is theta. Okay. Okay. How do I find what is the moment? Now, you should also agree with me that I can turn this into, well, it doesn't matter. Let's do this regardless. And this is not x anymore. I'm not looking at this. I'm just looking at this. So the normal force, so P, I can split it into two components. One along N and one along V. This is along N and this is along V. You agree? Now, if I had to split P into components, that would be N in this, V in this direction and N in this direction. Because if I sum V plus N, I get P. I don't need, though, I don't need to split P into components. I need the two forces that balance P. So I have to use the other way around. Okay, so this is a single force P and must be balanced by two forces N and V. So this is N of theta, and this is V of theta. Sorry, the other way around. Why am I always doing the other way around? This is N of theta, and this is V of theta. Okay? Now, where's the angle? Theta. In this drawing, theta is here. Where is theta here? This is 90 degrees, for sure. N and V are 90 degrees. So theta is either this or this. So which one is theta? Top or bottom? Alessandro says bottom. Do you agree? I do agree, because see, theta is made of the vertical and this thing, which is in the same direction. I mean, it doesn't look like so, but it should be the same direction as V. This thing and this thing are parallel. Actually, let me change this to be a bit more parallel. There you go. So yes, see, theta is made by the vertical, which is P, and this orientation, which is V. So this angle is theta. So how much is V? P, sine or cosine? P sine of theta or P cosine of theta? Guys, this is first year stuff. First lecture, first year, mechanical science, lecture 1.
Can you repeat the question?
V of theta. Is it P sine of theta or P cosine of theta? V of theta is adjacent or opposite to theta?
Cosine.
It's adjacent, so it's cosine. Right? So V of theta is P cosine theta. Come on, guys, come on. Come on, I fear for your exam. N of theta, of course, is P sine of theta. V of theta is P cosine of theta. We don't know the signs yet. The sign, see, n of theta is in the same direction as I wrote it, so that's positive. But v of theta is in the opposite direction. So that must be negative. Moment. What's the moment? M of theta. How do I find it? M of theta. We need to find force times perpendicular distance. The only force that we have on the right is P. Oh, Asham also said cosine. Good job. So we have P times perpendicular distance. Now, from here to here, that's L. Sorry, this is L. From here to here, this is L. 100%. But what is this distance here? How much is this? Because the moment is P times L plus that thing. How much is that thing? Second? V. Why V? We don't. This is geometry of the structure, so there are no forces involved. On the structure, what is that distance? It's R. So this distance is R. Okay? And this distance is also R. So, okay, Efia says R sine theta. And that is correct. Because you're looking at this edge here. Okay, and this edge is R sine theta. You agree with me? Good. So this is M of theta is P plus L plus R sine theta. So let me put this here. This is R sine theta. Okay, so P is force times perpendicular distance, so it's P times L plus R sine theta. Yes?
Why is V negative?
Why is V negative? Because see, in order to make it catch up around the polygon, I must draw it in this direction. But I originally drew it in this direction. So this is the positive convention. This is opposite, so that's negative. Okay? And M of theta is the moment, clockwise moment, that is counteracting this counterclockwise moment. So that's also positive. Positive as drawn. Not positive, because this is a clockwise moment, so it's a negative moment. But in the way I've drawn it, that's in the correct direction. That's what I'm saying. Any questions? Now, okay, now we can start using strain energy. So far, this was just first year stuff. Okay? So now let's go to the third year stuff. Third year stuff is strain energy. Now, total strain energy. What is the total strain energy of this structure? Is the total strain energy of the straight segment plus the total strain energy of the curved segment. So I'll say, let's call these with names. Let's call this point A, this point B, and this point C. And so the total strain energy, U total, is UAB plus UBC. Okay, so what is the total strain energy in segment AB? Let's have a look. Segment AB, we had no N. So we don't have normal strain energy. We have shear strain energy. Oh, what's going on here? We have shear strain energy, and we have bending strain energy. Again, let's say that we neglect shear. So we only have bending strain energy in this. Let's have a look at these. This is axial, shear, and bending. So all three. So ideally, this would be UAB axial plus UAB shear plus UAB bending plus UBC axial plus UBC shear plus UBC bending. Okay, now since I am of good heart, I would say the shear ones we neglect for slenderness, but in reality, you can only neglect the first one for slenderness. Second one is not slender, might not be slender. And to make the calculations easier, also because I believe that the tutorial question doesn't have EA at the bottom, see? Doesn't have any EA at the bottom. That means it's also neglecting the normal force. And so I'm neglecting also the normal force. So these ones are neglect on the grounds of slenderness. These ones are neglect on the grounds of simplicity, not correctness though, okay? You should also do that. So U total is the sum of the bending energy of both segments. That's what I'm saying. All right, do we need to calculate the energy or not? Let's look at the tutorial question. Tutorial question says, calculate the deflection. All right, all right. If I don't need the energy, I can use the simpler integration. Do you agree? Very good. So since I don't require we don't require the value of U tot, we can take advantage of this simpler integration. Okay. Oh, I forgot one thing. U total, remember this was a symmetric structure, so U total is twice as these, okay? Because A, B, and BC is not the entire structure, it's half of the structure. So the total energy is twice as much. So this is 2 times these. This is one of the common sources of errors and mistakes at the exam. You start by saying, yes, the structure is symmetric, then you forget to multiply everything times 2, as I did right now. So what is the simpler integration? Let me write it here. The deflection is the integral between 0 and L of m of x. I'm using just the bending one for simplicity, but you have to change this depending on what you're looking at. If you're looking at the normal energy, that's n of x divided by EA. Right? M of x over EI times the derivative of m of x in the P, in our case. In our case, that deflection is P. So we need to find first this term. So let's differentiate m of x with respect of P. We have 2 m of x's, one of AB, one of BC. So we'll do both. So the m of x, the MAB of x in the P is, let me have a look, from AB, this is AB, and this is BC. This one is P. The derivative of this, sorry, this one is x. The derivative of this with respect to P is x. Easy. Bam. And I'll shove it aside. The derivative of m of theta, in this case, we have MBC, and that was m of theta, with respect to P is, you should agree with me, is L plus R sine theta. If I take the derivative of MBC of theta, I get L plus R sine theta. Nice. Let me shove this a bit to the side. So this is a formula that you should remember. And these things are the ones that we found. Now, let's calculate the deflection as twice as much the integral between 0 and L of M AB of x over EI times the derivative of M AB of x over, in P dx. So this is segment AB plus this thing goes in brackets. Oh. Plus the integral. Now this was an integral in x. This is an integral in theta. You should remember that this goes from 0 to, so this is theta equals 0 is the vertical line. See, theta equals 0 is this line here. And we have to end here. So what's the angle? 90 degrees. 90 degrees, or even better, pi divided by 2. Remember, integration is in radians always. So from 0 to pi divided by 2 of MBC of theta over EI times the derivative of MBC of theta in the P r d theta. This is important, not d theta only, but r d theta, because ds, in which we had to integrate the curved beam, is in reality r d theta. So we have an extra r. That's very important. So don't forget about this. Let me highlight it so you don't forget about this. And then we can close. That's it. So this is twice this beast. And this beast is segment AB. And this is segment BC. Sorry, can you explain why it's r d theta again? Don't really get it. Okay, so let's say you have to integrate around this line. This line is a curved axis, S. So this is my S axis. And I have to integrate between 0 and the length. This is the length, L. So the integral should be from 0 to L of m of x squared over 2ei ds. Okay, and ds is this. Let me do it here. Let's say ds is this. So that's the idea. Now, this is very complicated because S is curved. It's curved, and so you don't know what a line integral is because you haven't done calculus 2. If you have done calculus 2, you know how to calculate a line integral. But even in that case, you will still go for that simplification route where you find, can I find, sorry, let me do this in another color. Can I find a relationship between ds and this angle theta? Because I know that this spans an angle. Okay, let's say this angle is 78 degrees, whatever. Okay, can I span this? Can I find a relationship between that and that? Okay, yes, it is infinitesimal theta. So what you find is this thing, as you just said, this thing, ds is d theta. So ds is over an infinitesimal theta. And so, of course, that means that ds is the radius times the angle r d theta. So every time you have to integrate in ds, you can integrate in r d theta. But theta is easy because it goes from 0 to L. This goes from 0 to L. You just have to change ds into r d theta and the extreme of integration from 0 to 78 degrees. Okay, not in degrees, of course. You have to times pi divided by 180 because you want it in radians. That's it. Very good. So I'm going to clear this. Don't need this anymore. There you go. All right, so now let's solve it. We have, oh, wow. How time flies when you're having fun. So integrating this, I get MAB of x is px. So this is delta equals twice the integral of px squared divided by I dx between 0 and L plus this is MBC is PL, it's plus P times L plus R sine theta squared divided by I times R d theta. Okay? So this one is quite easy to see. This one becomes P over EI times L cubed divided by 3. Can you see it? Because you have the integral of x squared there. Also, well, actually, if you want to do it step by step, this should be x cubed divided by 3 evaluated between 0 and L. Probably better if we add one more step. And this thing is, this goes from 0 to pi divided by 2. And then you get PL plus PL R over EI times pi divided by 2 plus R squared over EI times the integral of sine squared. No, that's not true. That's not true because this is squared. So this is L squared. And then you get the integral of PL R squared sine theta. Yes. Over EI d theta between 0 and pi divided by 2 plus the integral between 0 and pi divided by 2 of sine squared. So this is P r squared sine squared. So it's P r squared sine theta squared divided by EI. Okay. Now this one is simple because the integral of sine is minus cosine. And minus cosine of 0 is minus cosine. Okay, well, let's do this anyway. So this is P over EI x cubed divided by 3, 0L, plus P squared, PL squared R divided by EI times pi divided by 2, plus this one is PLR squared divided by EI times the cosine of theta, sorry, minus the cosine of theta, so I'll put it here. No, let's put it here. Minus cosine of theta evaluated in between 0 and pi divided by 2, and plus P r squared over EI. Am I missing something? Missing something? It's no, it's r cubed. That's not. It's r squared. It's r cubed, not r squared. Can you see why? Because this thing is L squared plus r squared sine theta squared plus RL sine theta. Okay, and then everything gets another R added to it. Okay. And we have to integrate the sine squared of theta. What is the integral of sine squared? I did remember it yesterday. I don't remember it now. So let's do the integral of sine squared theta. Integrate sine x times sine x in the x and sine. And there you go. It's this beast here. But if I do the integral, the definite integral, that gives me a better thing. So let's do the definite integral, which is this, of this. What? Between 0 and pi divided by 2. Sine x times sine x in the x. So this gives pi divided by 4. So all this thing here becomes pi divided by 4. Okay. So let me evaluate the first two. This is p L cubed over EI divided by over 3EI plus P L squared R pi over 2EI plus, now cosine of theta is 0, so this here becomes minus cosine of pi divided by 2 plus cosine of 0. Do you agree? And so this is 1, because this thing is 0 and this thing is 1. So basically, I can just say this thing is 1. And so we have PLR squared over EI plus PR cubed pi divided by 4 EI. This is the total. No, this is already the thing. I have to multiply it times 2. Okay, so this becomes 2/3. This gets the 2 away. This becomes times 2, and this becomes 2. This thing is delta. And hopefully, this is the correct answer. Let's check with the solution. But it looks correct, because this is EI is meter squared. EI is Newton meter squared. Divided by Newton divided by Newton meter squared, you get 1 over meter squared. Meter cubed over meter squared is meters. So this is meters. This is same units. See, these are just, instead of L cubed, this L squared R, this L R squared, and these are cubed. See how they line up nicely? They are all meters. When they expanded the brackets for the BC segment, why isn't there a 2LR sin theta? Oh, there should be a 2LR sin theta. Yes. So what I forgot, thank you, Efia. I think I screwed up one thing, and that is while I was doing this, I needed a 2 here. Okay, so overall, this is not 2 PLR squared becomes 4 PLR squared. This should be a 2 here and a 2 here, because this is the double product. It's L squared plus R squared sine theta squared plus 2 LR sine theta. 2 LR sine theta is this. Thank you. Yeah. So this thing is not this, but it should be 4. Yeah. So let me check the solution. And we have P over EI, or of course you can take this as a subject. So it's 2PL cubed over 3. This is correct. Yay. This is correct. Yay. This is correct. Yay. And this is also correct. I can't believe myself. Okay, so that's fine. And I was able to neglect EA because I looked at the solution, although it doesn't say, but the problem should really have stated, don't take into account any normal force. And I can see that it didn't take into account any normal force because I don't have any EA denominator anywhere. Okay, how was this? Fine? Not fine? So now you can do this at home, I believe. And it's also recorded anyway. So there is a solution video of this one. So I'll give you a break now because I think you deserve a break. Okay. We'll probably just sketch this solution here very briefly to see segment A, segment AB, segment BC, vertical one, what are the forces. Okay. All right, 5 minutes break and then we resume. Yes.
Noi avevamo questa submission per ieri e mi dà questo errore.
Hai sottomesso?
Prego?
Hai sottomesso, hai consegnato?
Sì, sì, sì. Però mi ha dato questo errore.
Penso che l'errore sia sul plagiarism report.
Sì, io ho chiesto a Reza, mi ha detto dovrebbe andare con Turnitin.
Sì, questa cosa qui viene riaggiornata ogni giorno. Ogni giorno prova a rigenerare il report.
Perché ieri mi dava questo errore, oggi
prova fino a domani.
Aggiornare la pagina.
Gli solo aggiornare la pagina, perché questo non devi fare niente. Questa qui è accettata. L'unica cosa che non ti sta dando è il plagiarism report.
Quindi è a posto.
Quindi la consegna è consegnata.
Comunque io ho avvisato anche Registry che non mi ha risposto nessuno.
Va bene, no, figurati. Ci vorranno giorni per rispondere.
E poi...
Vai.
So that's the whole idea. That was supposed to be like that. No, because they're both like that.
Per la 4, la parte B, Y, sì, questa qua, è la distanza
dalla prima origine che è praticamente la cordiata del centroide. Quindi questa qui. Il centroide non può essere più, il centroide deve essere sicuramente più su. Non può essere in mezzo a questo. Ok, hai un'altra parte più su.
Sì, sì,
un po' più spostato da su.
Però è più basso di questo qua.
Sì. È YC è questa distanza qui.
Tra questo e questo centroide.
Dal giù al centro. YC dovrebbe essere questa distanza qua. Questo è il centroide.
Sì.
Quindi YC è questa distanza qua.
Okay. E perché dopo ognuno la so, però dopo per questo qua si fa YA.
E questa è la distanza del punto A. Ma questa è la distanza del punto A. Cosa stai cercando qui? Questa è sigma B.
Sì, praticamente è quando è
Oh, sigma B è questo. Esatto. Questa è la distanza A. Quindi this is, perché vedi, sigma B è dove stava l'origine.
Okay.
Questa distanza che vai cercando tu adesso è questa qui.
Ok. Dal centroide, che è quello
Tu praticamente...
elastic plastic, giusto?
No, il centroide è quello elastico. Sempre.
Perché noi abbiamo un neutral axis. Okay.
Sì.
Poi c'è
Ma tu
neutral...
stai facendo plasticity.
Sì, sì, sì.
Unloading is elastic.
Okay.
Quindi devi trattarlo. Okay. Il neutral axis sta al centroide.
Okay.
Quindi devi ridisegnare la distribuzione. La distribuzione è bassa qui e alta qui, vedi? Quindi se fai questo meno questo meno 0, quindi qua è 0 meno qualcos'altro, Okay?
Sì, la loading quindi è completamente elastica e questa
Sì,
è...
quella dipende dalla plasticità che ha, insomma. Quello è un centro. Quindi quando fai questa cosa, i centroidi non stanno alla stessa altezza. Okay?
E questo è plastico come centroide?
Questo è elastic plastic, perché
Elastic.
plastico significa che il centroide sta nella bisettrice delle due aree.
Ok.
Okay? Quindi ogni volta devi vedere dove sta il centroide in questa condizione qui, dove è il centroide elastico, disegnare distribuzioni e fare tutta la sottrazione.
E poi questo qua alla fine è sempre il centroide elastico.
No, a quel punto non c'è più,
Sì, no, dipende.
non si chiama più in nessun modo. Cioè, ogni punto ha il suo residuo.
E si misurano le distanze da zero.
Qui perché hai trovato il centroide di questa cosa, l'hai trovata partendo da questa origine. Però se parti da un'altra origine, continui a misurarla dall'inizio.
Ok. Vabbè, grazie.
Eva, there's a reading list in Aula, I think. Okay, oh, sorry. So, Asham, is there a textbook? There is a reading. Yes, Eva, there is a reading list on Aula. What do you mean you can see one? I'll show you where it is. If you go on Aula, go to Essential, Module Guide. If you look at the module guide, which of course it doesn't show here, but if you look at the module guide, there you go. Readings. These are all the readings. Okay. So in this case, plasticity, Castigliano's theorem are found in this one. 3D stress transformations you'll find here, and some other things on plasticity. And this will be next week, fatigue of materials. And these are all dynamics. Okay? So this book cover much more than we do, really. But they are very, very, very good source of material. Yes?
I just got a question. This is for question 3 from the course.
Question 3 for the course. Yes.
This is for the...
You are BNG or MNG?
MNG. This is maximum diametric interference, and this is the minimum one. So I found this formula online, and I don't know if this is the...
Why are you looking to formula online if you don't know if they apply to your problem or not?
The thing is that I couldn't find one where it links pressure.
But you can do the calculations.
Yeah.
You can find the diametral interference, which is U1 minus U2 minus U1, so which is how much is the radial displacement of the inner fiber of the wheel, and how much is the radial displacement of the outer fiber of the shaft, and then you can find the radial interference, and that's a function of PC. That's it. So you can find the largest PC that you can get, the smallest PC that you can get, and that gives you the largest interference or the smallest interference. Okay.
For the maximum one, it said take into account factor of safety.
Yes.
And I posted a video from week 1, the YouTube. I watched a video on how he found this, and this is how he did it. So he drew this graph, and he said that tau max should be P over 2 equals to P over 2.
Tau max is sigma yield over 2.
Yeah.
So tau yield is sigma yield over 2. That's fine.
Yeah. So then
But the factor of safety is, it depends. What are you using? Tresca?
Yeah, Tresca, yeah.
So that the factor of safety for Tresca is sigma yield over sigma 1 minus sigma 3. So sigma 1 is the largest principal stress, sigma 3 is the smallest.
And sigma 1 minus sigma 3 is equals to, I think it's tau max over 2.
Yeah.
So is this the right way to do it?
So it's tau max times 2. Sigma 1 minus sigma 3 is the diameter.
Yeah. So that's
and this is 2 tau max.
Yeah.
So yes, that is good.
So then if I just sub
tau
in,
max sigma yield, it's twice sigma yield divided by tau max. Okay, so I don't know if this is what you've done. You've done this.
Then from this, if I find this is my pressure, so P over 2 is tau max.
No.
Or it's sigma 1 minus sigma 2.
Yes, that's sigma 1. So this is wrong. How can you tell this? This is wrong. So what you want to say is you start from here, find which one is your sigma 1 and sigma 3, which in your case might be hoop stress this and radial stress this. And if you have hoop stress minus radial stress, everything would be function of P. And then you can find P in this equation here, where P is your only unknown.
Yeah, right. Yeah,
Okay?
I get it. Yeah. Thank you.
Okay, guys, let's resume. It's raining outside. Is it raining? No, it's not raining. So let's let's go very quickly over question 3. Okay, question 3 says, this bar is fixed at one end and loaded by a moment at the free end. So it looks like this is very easy. Oh, it's only a moment applied at the free end, M. Determine, though, the horizontal and vertical deflection of the free end. Ouch. Ouch. Why ouch? Can we find the horizontal and vertical deflection of this point here using Castigliano's theorem? No. Why not? Because there is neither an horizontal force nor a vertical force applied there. So with Castigliano's theorem, I could find the angle, the slope of this point, at this point of that beam, because I have M. Since I don't have a vertical or an horizontal force, I have to apply dummy loadings. In this case, I'll use a dummy load for V. That would be my vertical force, vertical dummy force. There is a dummy load for H, which is my horizontal dummy force. Dummy loads. H and V. Because I want to find delta V and delta H. And then it's just a matter of, again, study this in segments. This is point A, this is point B, this is point C. So the total energy, U total, is UAB plus UBC, which is equal to U axial BC, sorry, AB, plus U bending AB, plus U axial AB, sorry, BC, so confusing, BC, plus U bending BC. Again, neglecting shear because shear is shear. Don't care. So on the grounds of slenderness, we say, okay, it's slender, it's very tiny. That's a wire, something like that. So it's very, very small energy in shear. And so this means, remember, this is B or A. Watch, how long is this? This is B and A. So this is B. And this is A, long. So this, you can find delta H as du total over dh, and I can find delta V as du total in dV, remembering that H equals 0, V equals 0, and H equals 0, V equals 0. Okay, so you have to remember these two things. In this derivative, after you've done the derivative, remember to set H equal to 0 and V equal to 0, because these are both dummy loads. Okay. So let's just explicitate the integrals. These would be, I'm going to use the simple integration. So for simple integration, I have the integral from 0 to b, because I'm looking at AB first, from 0 to b of n AB of x divided by EA times the derivative of nx, the derivative of NAB x in dh dx, plus the derivative of MAB of x EI times the derivative of M of x AB in dh dx, plus, so now I'm doing this, this is also from 0 to b, plus now the segment BC, the segment BC goes from 0 to a of n BC x EA, derivative n BC x in h dx, plus integral from 0 to a of n BC of x, sorry, m BC of x EI, derivative of m BC of x in the h dx. There you go. This gives you, is explicitator a real word? I hope so, because I use it all the time. So yeah, is explicitator a real word? Is it not? I mean, you tell me. I'm not native, so I make up words as I go along. So that's fine. All right, that's it. I mean, as long as the word is clear, it should be a word then. Okay. This one is basically almost the same, but it's exactly the same, really. So I'm just copy and pasting everything. But instead of this, we change all the H to V's. There you go. Solved. Well, kind of. Explicate. Yeah, but that explicate is not what I mean. When I say explicitate, which is not, it sounds odd when I say it out loud. When I say explicitate, I intend to make explicit. So make something explicit is not explicated, because explicate has to do with explain. What I'm doing is taking something implicit and making it explicit. So if you have a word for that, teach me a word for that. I'll be grateful. All right, so that's it for question 2. Oh, sorry, what question was this? Question 3. Question 3. Let's do question 5. So question 5 is, I lost it. There you go. It's the thing, I don't think there's a word for it. So we have a word like that in Italian. So why don't you have a word for it in English? I am sure there must be a word in English for that. Alessandro, am I right? Esplicitare?
I tried to explain that the other day.
See? Okay, so that's just an Italianism, okay? So use it as an Italianism or Latinism if you want to be a bit more ancient. Okay, guys, this was exactly the same as the question that I showed you as an exemplary curved component. Okay, so this should not be too hard. We've done this already in the lecture. At least m of theta, we found it in the lecture. In this case, I also want to find n of theta and v of theta. So let me draw this first. And this is a 3/4 of a circle, as you can see. and we have a rigidly secured at one end into an horizontal support. The remainder of the rod is bent to form a 3/4 of 150 mm circle. Free end is constrained to move vertically only. Okay. So we have here something that I can say it's a roller and a slider. And that slider slides in between two vertical guides. Second is something like this. I'll let the government know. Okay. So what we have here is a applied force of F. Is there an applied force of F? Oh, I just looked at it and I already forgotten. Oh, it's 220 Newton. Let's say it's F. Because we don't like numbers. If you need numbers, they are here on the side. That's it. What do we want to find though? Let me also find the center of this thing. And the radius. The radius being 150 millimeters. I remember this. This one. Young's modulus is given. So Young's modulus is 200 gigapascals. We have a 12.5 millimeters diameter rod. So we have the diameter phi is 12.5 millimeters. So we can find easily, we can find EI, say, if needed. We can find EA if needed. That's very easy. Find EI and EA. That's it. Yeah, I think that's it. There you go. So I can take this down and concentrate on this. So now we want to find, what do we want to find? The deflection of the free end, okay? So we want to find delta, and this delta is the vertical delta. So in this case, we don't need anything but other than just using Castigliano's theorem. That's very easy. What if I wanted to find the reaction force? Let's call this R. Okay, so let's make it a bit more interesting. I want to find R. How do I find R? Well, I know the delta H. Delta H is 0. We know that. So with this Castigliano's theorem, I can find du in dr, the derivative of the energy in dr, but that will give me delta H, which I know it's 0. So my unknown is not in the left-hand side, delta H equal to, my unknown is on the right-hand side. That unknown is R. Okay, so let's solve this first as the question asks, and then let's see if we can add the effect of R, which is probably not a good idea because you should probably do this first with both forces and then set R equal to 0. Okay, so we don't need the energy again, so we can use the simplified integration. This is a curved component, so we want to see what's happening when I cut, say, here. And I look left in this case. And of course, I also know that this thing is theta. So if I copy and paste this thing here, and I get rid of whatever is on the side here, Now this is R, and this is also R. Okay, so let's find n of theta, v of theta, and m of theta. Remember the internal forces that we are explicitating right now. They are m of theta in this direction, counterclockwise, n of theta in this direction, perpendicular to the cut, and v of theta in this direction, parallel to the cut, and of course perpendicular to n of theta. Okay, so V and N are the two forces that are balancing F plus R. Now, to do this, it's very complicated. So let's split F and R into their NV components, into a component along N and a component along V. Now, R is this force. So the N component is in this direction, and the V component is perpendicular and in this direction. Okay? Now, since I want the N component that balances, the N and V component that are balancing R, this is the V component, V of theta. I'm saying VR because that's not the entire V, because the entire V will have a component that is balancing R and the component that is balancing F. And this one is NR of theta. Where is the angle theta? On this triangle, where is theta? Theta is made by the shear force and the vertical. We don't have a vertical here. So, well, theta would be this, okay? Which is not part of our triangle. But you know that if this is this, this must be this. You agree with me? Because theta is made by the vertical and the shear, but theta is also made by the perpendicular to the vertical and the perpendicular to the shear. It's just rotating this angle 90 degrees. That's what I'm doing. Be aware, always be aware. Balancing is opposite. You're right. Thank you, Efia. Thank you again. So I was going in the wrong direction here because these are the components of R. I want the balancing forces. So this goes in this direction and this goes in this direction. Okay, thank you again. I must make sure that this polygon always chases its tail, because that means that the sum of these forces is 0. That means that NR plus VR are balancing R. Okay, and let me do the same for F. For F, sorry, F is going in the opposite direction. Why am I so distracted today? F is going in the opposite direction. There you go. And so we have N, let's say this component here in the direction N, and this component here in a direction perpendicular to N. We must make sure that these chase each other around. Okay, so this is NF of theta, and this is, of course, VF of theta. So see, V of theta in total is VF of theta minus VR of theta. Can you see why it's minus? This is in the same direction that I've drawn it. This is in the opposite direction. N of theta, though, is this plus this. Is N of F of theta plus N of R of theta. Yeah, but how much are these? Well, VR of theta is R sine theta. And then R of theta is, of course, R cosine of theta. Where is the angle here? Of course, we said earlier, the angle is made by the vertical and the shear force. So this is theta. And so N of F is F sine of theta. And V of F is F cosine of theta. Okay, so these things are all numbers. Well, not all numbers, they are all function of theta via sine and cosine. M of theta, though, how much is that? How do you find M of theta? Well, it's the force times distance. Now, in this case, we have two forces, R and F. So the moment is the sum of the moment of R plus the moment of F. And let's find the moment F with respect to this. The distance that we want is this one. How much is this? How much is that? If you notice that this thing is exactly this. You agree? It's the same thing. And so this is an angle with hypotenuse R and an angle of theta. So how much is this? R sine theta. Oh, it's my bad here because my bad of notation. I'm calling R and R the same thing. Okay, so probably not a smart choice of labeling. So let me change the label of this thing to small r rather than capital R. Because one is geometric information, one is a reaction force. So this one is, as I said, small r sine theta. Okay, so we have that M of theta equals minus, so see, this is in the same direction of the moment, so it's not balancing it. So this moment must be in the opposite direction in order to balance F. And it must be in the opposite direction in order to balance R. F is making it rotate in this way. R is making it rotate in this way. And so M of theta must be in the opposite way that I've drawn it. Do you agree? So otherwise, it's not balancing anything. So we both have negative values. One is negative F R sine theta. And the other one is R times this distance here. How much is this distance here? This distance here. How much is this distance? I'll give you 30 seconds to come up with an answer. How much is that distance? I see the emptiness in your eyes. How much? Cosine of what? R cosine of theta. I disagree because R cosine of theta is this distance here. See? This thing is R cosine of theta.
Small r minus r cosine of theta.
That is correct. It's the entire radius minus R cosine of theta. Yes, Roberts, that's correct. R minus R cosine of theta. Very good. I mean, took you a while, but very good. This thing is R times 1 minus cosine theta. Oh. Okay. So the moment is R times small r times 1 minus cosine theta. So we have again minus here. R 1 minus cosine of theta. Okay. This here. Okay. Forgive my poor choice of labelings. Now that you have capital R and small r, but I believe that we can understand this. Okay, this was the hardest part, really. Now it's all integration, which is not the hardest part. Okay, it's just the longer part. Do we need the energy? We don't. So we can already use the simplified integration. Simplified integration of a curved component. So we want to find delta V, and that is equal to the derivative of U total in dF, because F is the force that goes in the vertical direction. And this gives the integral of, so now again, let's not choose anything else other than bending. And if you want just bending, that means this is just m of theta divided by EI times the derivative of m of theta in F r d theta. And this goes from 0 to, this is 3/4 of a circle, so it's 3/2 of pi. 3 divided by 2 times pi. Nice. Let's do this. So dm theta df, this thing is, you should agree with me, r sine theta. Okay? Can you see it? Oh, minus r sine theta. So I can just do that entire multiplication there and so on and so forth. Let's see if we can do this with Wolfram alpha. But even better, now let's do it. Let's do it anyway. We have time. We have time, so let's do this. At some point, could we go through the 206 exam? 206 exam Q4 from last year. From last year. Last year. What's the 206 exam question for?
It was the question that after
Okay, I'm not sure. None of us could do it. It was so hard. Oh, all right. Yeah, at some point, yeah. If you submit it to me, I can show you how to do this. But it's okay. That's an odd request, though. It's a specifically, oddly specific request. Okay, so let me write the equation. So this is the integral between 0 and 3/2 of pi of minus fr sine theta squared minus r squared sorry, plus again, r squared times 1 minus cosine theta sine theta. So possibly something like this. Divided by I, that I will place outside, in r d theta. No, this is not capital R, this is small r, remember, where the geometric r is this, so this becomes r cubed, d theta. Okay, looks very complicated, but I think it's fine. Should not be too hard. So this one becomes 1 over EI times f r cubed times the integral of sine squared. The integral of sine squared, we did it earlier, it was x minus, the integral of sine squared between 0 and 3/2 of pi ¾ of pi plus r cubed times the integral of sine theta. I'll do this very easily. The definite integral of this is 1 minus cosine of theta sine theta guys, 1 divided by 2. So minus r cubed divided by 2. So that's dv. Now, is this dv? Oh, also, we can rewrite this. See, this is r cubed minus r cubed divided by 2. So I can just simplify this by saying this, okay? Do you agree with me? Now, this is delta V, but remember that delta V also needs R equals 0, because that was our dummy load. Okay, so that means that this is 0 because of our dummy load. And so the deflection is equal to F R cubed. So 3/4 EI F R cubed pi. And all these things are numbers here, see? We have all the numbers. And so you will end up with a number here that is, or at least it should be, 7.2 millimeters. Now, it's not requested, but since we have done all this thing, let's calculate the reaction force. So what is the reaction force to keep that thing to slide horizontally? Okay, so this should not slide horizontally at all. This point will only move vertically. So that means we are using, we have a, yes. Why am I using it as a dummy load? What do you mean, R? I just use it because I want to find R. And so if I want to find R, I have to make it explicit.
In this case, why did you set it to 0?
Oh, because it's not 0. You're right. You're right. There's non-zero. Sorry, you're right. There's non-zero because it's not a dummy load. It is a real reaction force. Thank you. Okay, so this is non-zero. And so you need to calculate this then, and this is not a number yet, because we need to calculate the reaction force first, because you can't calculate this if you don't have R, because you have two unknowns here, delta V and R. So let's calculate R, and let's calculate R by finding delta H, which is equal to 0. Delta H is equal to 0, but delta H is also equal to the integral between 0 and 3/2 of pi of dm theta ei times, sorry, not d, just m of theta di, m of theta over ei times dm of theta in the r, which is r d theta, which is equal to, now let me do this thing all over again. So this is exactly the same. No, it's not the same, because we have to find dm over dr. So dm theta in dr, this is 1 minus cosine of theta. So r times 1 minus cosine of theta, negative. Okay. Good, good. What else? Well, we have to do this calculation now. So let me copy this so I can look at it while I draw it, and that's the integral. So 0 equals the integral 0 and 3/2 of pi of minus f r squared times sine theta minus sine theta cosine theta minus r squared times 1 minus cosine theta squared, r d theta. Now this r gets me all these squared to cube, and there you go. Okay, don't need this anymore. Do you agree with me? Is this? Can you please triple check my calculations, because it's not my day today, apparently. It's one of those days, and hopefully it will be not one of those days at the exam. I am missing EI, I know that. That's fine. I'm missing EI, but I don't care if I miss EI, because see, I have equal to 0, so I can multiply everything times EI, and it goes away. That's easy. So let's solve this. So this is 0 equals, well, I'll flip the equation over. So I'll say this equals 0. Okay. And so I'll say that 1 over EI times minus fr cubed times the sine theta between 0 and 3/2 of pi. That was 1, I believe. I think that was 1. Yes, so this is 1 minus fr cubed. This is plus this thing, which is half, plus half of this, minus r cubed times 1 minus cosine theta squared. Come on, 1 minus cosine theta. So this is 1 minus, no, 1 minus x squared. 2 plus 9 pi divided by 4. Okay. Equal 0. See now, what's my only unknown in this equation? R. R is my only unknown. I told you that if you set your Castellanos theorem equal to a quantity, it gives you the force that is required to make that happen. So this is the force. F is a number. Remember, F is 200 newtons, 220. F is this number. So this is given. Young's modulus is given. I mean, this we don't care, because this equation becomes just R equals this one. I can also rewrite as, so this thing is just F minus FR cubed divided by 2. Okay? So R is just FR cubed divided by 2. This goes on the other side. Divided by R cubed. That goes away. Divided by 2 plus 9 pi divided by 4. And of course, negative, because this goes on the other side. This is negative, goes on the other side, isn't it? Yes, yes. So in the end, R is F, so minus F divided by 2, divided by again, so it's times two, but in this case it's just 4 times 9 divided by 2 times pi. Nice. So how much is this? Minus 220 divided by this number. Let me check it. This is minus 220 divided by 4 plus 9/2 of pi minus 12.12 minus 12.13 newtons. Not a lot. And it makes sense because that point was already on a vertical path, more or less. Okay, so you don't need much force in order to keep it in place. Also, it's negative because it's not going in this direction as I originally said, but it's going in the other direction. Can you see why? Because that point will tend to open it. Okay. So R, it's keeping it from moving. Okay, any questions? No questions? No questions. Online? Did I snipe you all with my sleeping darts? I know that on Tuesday I sniped you all. Almost all of you are just. It's fine. I can. I guarantee that is the most boring lecture was last Tuesday. Okay? From now on, everything will be much faster and nicer and not much more integration at all. Okay, which is a bit of a shame, but it's probably better for your attendance. No questions? No, looks like not. So we have. Why is it a shame? Why is it a shame? Because I think you need more integration time. Yeah? How are you combating inflation? What? No, you really need more integration, because integration is basically, it should be the bread and butter of engineers. Because we engineers, in order to solve a large problem, we look at the tiny problem and then we integrate over the entire span. That's how it works. Imagine you have a mechanism, whatever. When you do the velocity diagrams or acceleration diagrams of a mechanism, you're looking at that in that specific instant of time. At the next instant of time, that's changing. So in order to find what is the span of the entire mechanism while it's moving, you need to integrate over the 360 degrees angle, say, of the crank. If you integrate over the entire 360 degrees of the crank, you'll see what's happening to the piston, say, during one entire cycle, and you'll find the entire velocity profile of the piston. From the acceleration profile, you find the entire velocity profile of the piston, and you find the displacement profile of the piston. And so you know how much the volume of the chamber of the internal combustion engine is changing over time. And if you know that, you can find how the pressure in the chamber is changing over time. And if you know the specific heat of whatever combustible you're using to drive the engine, you know how that impacts on, see, all these things all just come from integration. I understand that this is very haunting. It's not, you don't like it because it's complicated. But that's, I think that calculus in particular is how nature speaks to you. Okay. And yes, Asham should have chosen business and finance if they really want to know how to combat inflation. Ideally, you should invest in something that has a larger interest rate than the inflation gives you over the year. I mean, so it was energy in, energy out, money in, money out. So inflation is eroding your savings, but if your savings give you more money than they are eroding, you are combating inflation. But that's just on you. Okay. Don't invest in shady companies. Don't invest in companies that don't like your future. Okay. Don't invest in companies that pollute. Don't invest in companies that have slave labor. Don't invest in companies that are unethical. Okay. Because those are the companies that give you the largest yields. But if you invest in those companies, you are complicit. Okay. Don't want to be complicit of slave labor, especially. As we cry over solids. Also, don't do anything with NFTs, okay? NFTs are scam. No, don't do anything with NFTs. NFTs are a scam. The scam of NFTs is that you buy NFTs with real money. So whoever has Bitcoin, or Ethereum in that case, has more money to exchange Ethereum with real money, because that real money comes from you, gullible people that are buying a block on the blockchain. Okay. So if you pump money into this system, you are making the rich people more rich, and you are the proud owner of a digital certificate on a blockchain. That's really a scam. Okay? 100% scam. Don't do that. And this is being recorded, so I probably have to cut this thing out of the recording as well. Yes.
Question again. Why is the moment negative?
Because as we have drawn it,
Yeah.
we have drawn it in the clockwise direction.
Yeah.
And both of these are clockwise as well.
Yeah.
So if this is clockwise as well, everything is clockwise, and it doesn't.
So why do we consider these two in the same direction and this one in the opposite?
See, this is best if you just write the equation. If you write the equation says that m of theta, minus m of theta clockwise, minus r times this clockwise, minus f times this clockwise equals 0. And so in order to find the m of theta, you take this one on the opposite side and becomes.
Yeah.
positive. This is exactly the same. So you have n of theta
Yeah.
plus nr of theta plus nf of theta equals 0.
Yeah,
And so this should be negative. You're right.
Both of them, right?
Yes, both of them. Thank you.
Okay.
Yes, because this must be balancing. Yes.
And this is the other way around then.
And this one should be,
V.
this is v of theta minus vr plus vf equals 0. So yes, this is also the other way. Ah,
Good.
thank you.
Thank you.
Again, this was not my day today. So many things.
No, it was just going like in my head, it didn't make
Okay,
sense.
it's fine. But we have them here now.
Right.
They have been captured. Thank you.
Thank you.
No worry. Yeah.
Okay,
Yes, how's things?
not bad. So for this question, you
Yep.
know how it says to calculate the deflection for the first one?
Yes.
How are we meant to calculate it if you don't know the reaction force?
You know the force.
The reaction force. Because in the
You have to calculate the reaction force.
oh, so you have to do it that way anyway.
Yeah.
Alright,
Okay.
thank you.
All right. Did you see people sell Coventry exam papers online? Really? Are they selling exam papers online? Not mine, for sure. Are they selling online? Let me stop recording.